Hello everyone, my name is Xi Zhang from Shanghai Jiaotong University. This tutorial focuses on the interpretable machine learning. It's very difficult to say current XI studies are science, but there are still some efforts that pushes XI studies towards the direction of science. Thus, in this tutorial, I will introduce some recent studies in our group in this direction. Let's first summarize the current state of XI studies and vision of XI science. Okay, the first problem is that why the XI is so important. This figure shows the growth of the paper number recently in XI. In recent year, you can see the paper number grows so fast. So, if you only focus on some typical problems such as object classification, for example, in the ImageNet dataset, whether a model or whether a DNA is explainable or not is not so important. But if you focus on some very important applications such as finance, autonomous driving, medical diagnosis, and the military, the interpretability of a DNA is very important in this case. In general, we can summarize topics of explaining DNAs into following two types. The first type is schematic explanation. It means that people want to schematically explain the knowledge that is encoded or trained DNA. The second direction is that is the mathematical explanation. That means people want to mathematically prove or explain the representation capacity of a neural network. The basic idea for schematic explanation is to verify whether a model encodes correct reason or not, encodes correct features or not. For example, when the neural network classify whether this girl wears lipstick or not, it's supposed that the neural network are supposed to use the mouth feature for classification. But when we visualize its attention, we find that the neural network actually uses the eye features, even the hair features, not only the mouth feature. And on the other hand, for the classification of the horse, we find that the neural network uses the text on the corner instead of using the shape of a horse. They are all problems. And another application is that when the neural network make a prediction, we want to clarify the true reason behind the prediction. For example, for the medical image, the neural network says that this guy needs a surgery, and the score is 0.9. And the reason may be like this. The network detects a problem in this place, and it contributes 0.2, and it detects another problem in the second place, it contributes 0.1, and it may detect the third place, third problem, and it contributes 0.6, said like this. So we can clarify the reason behind the prediction score. In general, we can classify all topics in XAI, all topics in the schematic explanation of neural network into the following 5 directions. First, people want to answer which schematic concept modeled and used for prediction. Second, people sometimes want to quantify and improve the trustworthiness or the safety of a neural network. Third, people sometimes need to end-to-end learn a neural network in which features are interpretable to human beings. Based on this study, based on the interpretability of features, people may even communicate with the neural network and let the neural network learn at the semantic level, where the communication with the human beings. And the final issue for the schematical explanation is how to evaluate the explanation, because we do not know the ground truth explanation for the network. So the evaluation of the explanation is very important but very challenging issues nowadays. Besides the schematical explanation of deep learning, the mathematical explanation representation power of the neural network is also important. For example, sometimes people want to model and explain the representation capacity of the DNA. Sometimes people want to explain the effectiveness of the current deep learning technologies, such as knowledge distillation, adversarial learning, and network compression. Third, how to bridge the network architecture with the knowledge representation. Nowadays, people only search different architecture for the neural network and to test its performance. But how to mathematically bridge the architecture and its performance is very challenging issues nowadays. Finally, how to debug the problem inside neural network. Instead of fine-tuning the neural network using massive training samples, how to correctly localize the problem inside the neural network to identify which parameter is problematic, which parameter is responsible for the error of the neural network. So, and we can fix it just like debugging a code. This is a very challenging issues for deep learning. This slide discusses the problems of current schematical explanation of neural network. Many methods of schematical explanation of neural network can be still considered as heuristic technologies rather than the science. So there are 4 aspects. First, this study usually can only ensure self-consistency instead of the mutuality between different explanation results. So the explanation result of one method cannot verify the explanation result of the other method. This is a big problem. So how to ensure the trustworthiness of the explanation? Second problem is that we lack solid theoretical foundation for the explanation. Although we have some foundations, but they are not enough. They are far from enough. Third, it's very difficult to use the current explanation results to improve the performance of DNNs. Fourth, now this field lacks convincing enough evaluation metrics to evaluate the quality of the explanation, because we have no ground truth explanation. Binking has found that many existing attribution-based explanations seem like the edge detections. On the other hand, for the explanation of the representation capacity of the neural network, we still have much work to do. For example, nowadays, many methods are limited to certain assumptions. For example, they only focus on the shallow nets or some network with infinite width. And second, sometimes some people mathematically prove the bound of the generalization bound, but the mathematical proof is still not equivalent to the schematical understanding. And third, current study cannot explain the emergence of the semantics in deep layers, because unlike other models, unlike the shallow neural networks, the deep networks, the unique feature is that sometimes the semantic emerge in deep layers. Although the current XCI study is still far away from science. Let me share my own vision for Xci science. I think it should consider three aspects. First is the regional explanation with strict meanings, because many people use the concepts, some existing concept to explain the knowledge inside neural network. For example, the visual concept and the linguistic concept. Let's just take the visual concept, for example. We need to ensure the strictness of the visual concepts. And sometimes people need to clarify the compositional visual concept that is encoded in the intermediate layer of the neural network. So the first aspect is that we need to ensure the strictness of the visual concept, of the concept that are used to explain the neural network. The second is that we need some more metrics for the repetition power of the neural network. For example, to explain the repetition, to explain the generalization power, or to explain the robustness of the neural network, we need new metrics. Third, we need some well-proved theoretical foundation for the explanation. For the last two aspects, I think the people need sometimes we need to think about the mutuality between different metrics. For example, we need to consider the relationship between the feature transferability and the feature adversarial robustness and the transferability. And we need to consider the adversarial transferability and the interaction. What's the relationship between the adversarial transferability and the interactions? And sometimes we can prove the relationship between the transformation complexity and the feature disentanglement. And sometimes we can prove the relationship between the interaction of input variables and the generalization power of the neural network. So in this case, if different explanation metrics or different explanation methods can verify each other, we will get more trustworthy explanation results. Second, sometimes we need to discover and mine some instance of existing deep learning methods. For example, we need to summarize the effective factors from some ad hoc technologies. What's the core or essential factors that are effective for this task from the existing ad hoc technologies, and how to improve the existing methods. Finally, I think if XAI is a science, people need to use the explanation result to guide the deep learning. For example, to guide the design of network architectures and to guide the learning process. Then I will introduce some previous studies on both the strict explanation of neural network and on the fine-grained explanation of neural networks. First, Shapley value. The Shapley value is defined in game theory. To compute the Shapley value, let us consider each input variable of a DN as a player. And let us consider the scalar output of the neural network as the total reward earned by all the players in the game. That means the total effects of all input variables. So the Shapley value is designed to finally allocate the contribution of each player. That means the Shapley value estimates the importance of the attribution of each pixel to the prediction, to the classification result. So we can consider the Shapley value of each input pixel or input word as the importance or attribution of this pixel or the word. The Shapley value is widely considered the standard unbiased attribution or importance of each input variable when we explain neural network. It's because it's the unique solution that satisfies the desirable properties The Shapley value satisfies the following four desirable properties, including the linearity property, the dummy property, symmetry property, and efficiency property. This property ensures the objectiveness and the trustworthiness of this of the estimation of the attribution. And the remaining issues for the Shapley value is that when we compute the Shapley value, we need to determine the reasonable inference, the reference value for each pixel, and we need to determine the reasonable partition of the players. How to determine the reference value and how to segment the entire image to different players is still an open problem nowadays. The Shapley value estimates the importance of each input variable over DN. Then, let us focus on the interactions between different input variables. For most AI tasks, for example, for the classification of the image or for the classification of the sentence, the input variables do not work individually. Instead, they cooperate with each other to form some inference pattern to make the prediction. So, let us focus on the interactions between input variables. We can define the interactions based on Shapley value, based on the importance of each input variable. Let us consider the importance between two variables, A and B. Their interactions can be defined as the change of the importance of A when B is present, with respect to the case when the importance of A when B is absent. So that means if the presence of a B will change the importance of A, it means they have interactions. So we can define the interaction of the between A and B using this equation. Then further, we can extend the standard interaction between two players into the multi-order interactions. The multi-order interactions indicate the interaction between two players when we consider different contextual players or different number of contextual input pixels. The high-order interactions usually describe the more complex patterns, and the low-order interactions usually describe the features of some simple context. And this equation is the standard definition for multi-order interactions, and this definition satisfies the following 7 properties. And these properties ensure the trustworthiness of the interactions. This slide discusses the relationship between the interactions and the representation of visual concept. As I introduced before, the lower the interaction is computed considering the contextual relationship with very few pixels. So the low-order interaction usually represent some simple features, such as edges and colors. And the middle-order interactions are computed using more contextual pixels. It means the middle-order interaction reflects some complex features, for example, some complex structures of an object. And the large-order interactions usually indicate some global structure. That means, for example, the sky or the grassland or the sea is a very large-scale textual information. Or sometimes the high-order interaction represent the memory of the outlier samples, and sometimes it represents the noisy patterns. Beyond the multi-order interactions, we also define the multivariate interactions. Sometimes we can consider the multivariate interactions as the prototype features to understand the behavior of DNN. The multivariate interactions indicate the interaction between multiple input variables. If the network makes an incorrect prediction, we can extract the multivariate interactions of the input sentence. inside input sentence to explain the reason or to explain the calibration between the words that are responsible for the incorrect prediction. In fact, there are many other ways to define the interactions between input variables. In this slide, I show another way to define interaction, namely the sharply tailored interaction in text to define the interaction between multiple variables, which can be used to explain the neural networks. Previous slides show some theoretical foundation to ensure the strictness of the explanation. And in the following slides, I will show some technique to obtain the fine-grained explanation, the regional fine-grained explanation of the neural networks. Previous studies have analyzed the distribution of different visual concepts encoded in convolutional layers, and also visualize the semantic concept in each specific convolutional filters. And but what we want to do is that we want to answer how many types of patterns or visual concepts are mobilized by a single convolutional filter over the CNN. For example, this is a feature map of a specific layer of a specific filter. This is a single channel over the feature map. This is the specific channel of feature map. I visualize the distribution of activation in the feature map in this channel. This channel is activated by both the hand and the branch. And also for the same filter or for the same channel, given different input images, the filter was activated by different concept. Sometimes in the first image, it's triggered by the branch. The second image is mainly triggered by the torso of the bird. And this image is triggered by the hand. This image is sometimes triggered by the tail, sometimes triggered by the partially triggered by the tails, partially triggered by a branch. So you know that for a single filter, it usually encodes a mixture of representation. It encodes a mixture of visual concepts. So the core issue is how to disentangle different visual concepts from a single filter. The second problem is that how to model the relationship between different concepts. For example, there are 3 channels over a single layer. And this is the 3 channel of the feature map. It have different activation peaks, but on the left, the 3 activation peaks co-activate with each other, and they represent the hand part of the horse. Third, what's the spatial relationship between the co-activated patterns? So, in this study, we propose an explanatory graph as a dictionary to explain the pre-trained neural network, to explain the visual concept encoded in a pre-trained convolution layer. The graph have different layers. Each layer corresponds to a single convolution layer in the CNN, and each node represents a single part. For example, when this node triggers, it always represents the mouth of a horse, and this node always represents the ear of the horse. And a single filter, we may disentangle multiple different nodes. We may disentangle multiple different visual concepts from a single filter. That means, for example, this filter, we can disentangle the pattern for the both hand and disentangle the pattern for the neck, both the hand and the neck. And the edges represent the co-activation relationship and the spatial relationship between different nodes. So in sum, we can consider the explanatory graph as a dictionary for all potential visual concepts encoded in the convolutional layers. Given a certain input image, maybe only 5% of the concepts are triggered So we can use the graph to assign a certain visual concept for each peak in the feature map, and to explain the semantical meaning behind the semantical meaning of these new activations. The input is a pre-trained. We can use a method to explain either the AlexNet or VGG16 or the residual networks. Note that we do not need any annotation of paths or textures to learn the explanatory graph. We just let the algorithm automatically summarize some object paths knowledge from the pre-trained neural network, because we do not want to let the human being to teach the explanatory graph how to explain the neural network. I just want the graph to automatically learn some obvious patterns from the neural network. So the output is an explanatory graph. This slide shows our explanation result. On the right, I show the chaotic feature maps of the different filters. On the left, I show the nodes disentangled from the filters. Each node represents a clear semantical meaning. For example, node 1 is disentangled from a certain filter. It always represents the hind part of the bird. Node 2, it always represents the dorsal part of the bird or the feet part of the bird. Node 3 is disentangled from another filter, but it also represents the hand of the bird. So you can see our method can ensure the clarity of the semantical meaning for each node. We can disentangle the clear semantical concept from the chaotic feature maps. Then I introduce the automatically learned interpretable filters. In traditional neural network, the feature maps of a single filter is very chaotic. It will represent multiple visual concepts. But in this study, want to end-to-end learn a neural network without any additional pattern annotation. That means we want to learn a neural network in which each filter represents a specific object part, but we do not use any additional pattern annotation. We want the neural network automatically learn such visual concept. So in the interpretable neural network, I want each filter represent a certain specific part of the object. This filter obviously represents the hand part of bird. This filter mainly represents the dorsal part of the bird. It needs to automatically learn such visual concept. The solution is very simple. We simply add a certain loss, namely the filter loss, to each channel of a specific feature map or a specific layer. The filter loss just pushes the feature repetition of a single channel into the repetition of a specific object part, but this loss do not need any annotation of the object parts. The filter loss is formulated as a minor mutual information between the feature map of this channel and the predefined template. The template do not have any semantical meaning. It just indicate the different position, the different activation position in the feature map. So this loss ensures that each feature map, each channel should only have one activation peak, but we do not control the position of the activation. So this loss ensures that each channel only represents a single part of the object. So this is our result. You can see we learn the CNN to classify different animals, but we do not label where is the hand, where is the torso. You can see our method can automatically let the different filter learn different part. And we can find that for most filter it learns the hand part of the animal. Maybe the hand part is the most discriminative part for the classification. But for the zebra, it encodes the texture on the torso, because for the zebra, the texture is the most discriminative feature. Besides the schematical explanation of the knowledge encoded inside the neural network, some people want to quantify the representation power of the neural network. In our previous studies, we proposed different metrics to quantify the representation power of the DNA from different perspectives. The first perspective is to quantify the layer-wise and pixel-wise information discarding in DNs. We hope to measure the information encoded in intermediate layers as a general metric. We use this metric to show the information processing behaviors in deep models. And we use the metric to explain existing deep learning technologies. For example, network compression, knowledge distillation, and the modification of the architectures. We can consider the entire neural network as a layer-wise discarding of the input information. For example, in the low layer, the neural network may discard a certain proportion of the information of the input pixels. And in the high layer, the neural network gradually discards more and more information. But the neural network usually discards less foreground information, but discards more background information. In this way, to ensure reliable predictions. So we propose two metrics to measure two types of information discarding. The first metric is to quantify how much information of the input is used to compute the feature. Second is how much information of the input can be recovered from the feature. These two metrics are very similar to each other, but not equal to, but not the same. When we quantify the representation power of a neural network, a good metric is usually supposed to enable fine compressions between different neural networks, or sometimes we need to enable the fine compression between different layers of the neural network. But previous metrics such as the gradient-based or the perturbation-based metrics usually cannot enable such fine compressions between different layers of neural networks or between different DNs. But in compression, here we show the heat maps for information discarding through different layers. This is the heat map for the first type of metric. This is the second type of information discarding. Compared to previous metrics, our metric enables fine compressions between different layers, fine compression of the representation power of between different layers inside a specific DNA. And this metric also enables fine compression between the different DNs. And we can use a metric to analyze the information behavior of each DNA. We use our method to explain the success of the BERT model in NLP tasks. The horizontal line indicates the different words in the input sentence, and the different color shows the importance of different words, and the different rows indicate the importance estimated for different models. You can see the LSTM and the CNN usually can only detect a range of important words. A sequence of words can consider the entire sequence of words as important words. But the BERT and the transformer can accurately select individual words. And because the BERT is much deeper than transformer, it usually selects much more words than the transformer. And in the below figure, we can see in which layer the DNA can distinguish important words away from the unimportant words. Furthermore, based on the information discarding metric, we further propose a method to quantify or to count the number of knowledge points that are encoded inside the intermediate layer of a pre-trained neural network. Before this study, there are no metric to count the number of knowledge points encoded by a neural network. Now we can use the number of knowledge points to explain the success of knowledge distillation. More specifically, we want to verify the following three hypotheses. Compared with the learning from scratch, knowledge distillation can learn more knowledge and can learn more diverse knowledge. And compared with the traditional learning from scratch, knowledge distillation suffers less detour in learning, can directly learn the target knowledge. Then I introduce the second metric. This is the knowledge consistency between different neural networks. As a generic metric, knowledge distillation can be used to quantify and evaluate the reliability of the features inside a neural network. And this metric can be also used to boost the performance of neural network without any additional annotations. And this metric can also be used to explain the success of existing deep learning technologies. For example, the knowledge distillation, the network compression, and the adversarial attacks. Let us train two DNNs for the same task. And Xa indicates the feature of DNA, and Xb indicates the feature of DNB. If Xb can be reconstructed by Xa via a linear transformation, we call the Xa and Xb are zero-order consistent. If Xa can be reconstructed by Xb can be reconstructed by Xa via a single nonlinear operation, we call Xa and Xb as one-order consistent. So in this way, we can decompose Xb into k+2 components, including the zero-order consistent feature component, the first-order consistent feature component, and the kth-order consistent feature component, and X delta. X delta indicates the inconsistent feature component. And we find that the consistent feature component usually indicates the reliable features. And we can use the consistent feature component to further boost the performance. And we can visualize the feature component of different orders. You can see the low-order consistent feature component usually represent the main part of the object, and the non-consistent feature component, the inconsistent feature component, usually represent noises. We can also use the knowledge consistency between different neural networks to disentangle the blind spot and unreliable features from a neural network. The knowledge consistency between neural networks can be also used to quantify the stability of the learning. That means we can use this metric to quantify the risk of overfitting. If we use the same training samples to learn the same neural network 2 times, if the knowledge consistency between the two neural networks is very high, it means the overfitting risk is very low. The lower knowledge consistency indicates the high overfitting risk. Furthermore, we can use the metric of knowledge consistency to remove redundant features and boost the performance of our pre-trained neural network. If the neural network is pre-trained for massive categories and is further fine-tuned for very few categories, then many features encoded inside this neural network may be redundant for the target task. So we can use the knowledge consistency to remove such redundant features and significantly boost the performance. Then introduce the third metric, the feature and transformation complexity of a neural network. In our previous studies, we have defined two types of complexities for a neural network. That's the feature complexity and the transformation complexity. Then we have explored the relationship between the complexity and other metrics, such as feature reliability, the generalization power, and the feature disentanglement. First, the feature complexity. Given an intermediate layer feature of a pre-trained DNA, the feature complexity is defined as the minimum number of nonlinear layers that's required to compute this feature, using another benchmark DNA with a fixed width. Based on this definition, we can further disentangle the intermediate layer feature into feature components of different complexity orders. You can see the simple component usually correspond to the global shapes, and the complex component usually corresponds to object details and noises. Then we find out that when we increase the number of training samples, we can significantly boost the commonness or the reliability of the learned features, but we cannot significantly increase the complexity of a feature component. Then we find that feature components of different complexities may have different impacts on the classification task. We find that the feature component of the complexity of the half depth is usually the most effective to the classification. And complex features are not, the most complex features are not always the most effective. We can reduce the significance of overfitting of low complexity feature component by adding more training samples. But for a high complexity feature component, their overfitting level is insensitive to the sample number. Because feature components of different complexity have different impacts to the prediction, we can disentangle the most effective feature component to boost the classification accuracy by 5%. The second type of complexity is the transformation complexity. It measures the complexity of the transformations that are used by the neural network for prediction. So in this study, we just quantify the entropy of the gating state of ALU layers, of all ALU layers in the neural network, as the transformation complexity. We define three types of transformation complexity. First is the entropy of gating states of all ALU layers. Second is the mutual information of gating state and the input. And third is the mutual information of the gating state, the input, and the output. Then we further prove the negative relationship between the feature disentanglement and the transformation complexity. That means if a neural network encodes more complex transformations, then the neural network will generate more disentangled features. Then we explore the maximum complexity of a neural network. When we use the same neural network to conduct different tasks, some tasks are simple, some tasks are very difficult. So we gradually increase the complexity of the task and to check whether the transformation complexity encoded by the neural network also increase. We find that the transformation complexity does not always increase along with the increase of the complexity of the task. Sometimes when the task is very complex, then the transformation complexity is saturated and begin to decrease. Maybe the limit of the transformation complexity of the neural network is due to the optimization power of the neural network. Finally, we find that the overfitting level of the model is very related to the transformation complexity. So we propose a loss to directly penalize the transformation complexity of the neural network. And we can use this loss to reduce the complexity and at the same time, the gap between the testing loss and the training loss is also reduced. Then I introduce the last section of this tutorial, the proof of the mathematical essence of existing deep learning methods. It includes the essence of methods of boosting adversarial transferability and the essence of dropout operation. We also use the aforementioned game-theoretical interactions to explain the essence of dropout operation and to explain the essence of the adversarial transferability. The game-theoretical interactions describe the interaction between input variables such as input pixels and input words, so to describe their cooperative relationship between different words and pixels. The explanation of the dropout operation has three aspects. First, we theoretically prove that the dropout operation can decrease the interaction strength that is modeled by the DNNs. Second, we prove that there is a negative correlation between the strength of interactions and the generalization power of the neural network. Third, based on above findings, we develop a new method to control the strength of interaction in order to control the generalization ability of the neural network. This slide shows that the dropout operation can decrease the strength of interactions modeled by the DNNs. It also shows that when we penalize the interactions, we can boost the performance and reduce the overfitting level. More specifically, we propose a loss to penalize the interaction. And this loss can accurately control the DNN between the overfitting and underfitting. In comparison, the traditional dropout operation cannot accurately control the overfitting level of the DNN. On the other hand, the interaction loss also solves the problem of that the dropout is not compatible with the batch normalization. The proposed loss is incompatible with the batch normalization. This slide shows how we use the interaction loss to accurately control the DNN from overfitting to underfitting. Then we further prove the negative correlation between the interaction and the adversarial transferability. We find that the multi-step attacks are usually generate more interactions than the single-step attacks. And the multi-step attack usually more overfitted to the source model and suffer from the low transferability than the single-step attack. So we have an assumption that the interaction is negatively correlated with the adversarial transferability. The negative correlation between the interaction and the transferability can be verified from different perspectives. First, among all the previous methods of boosting adversarial transferability, most of these methods, we can prove that most of these methods actually decrease the interaction between input variables. And we can theoretically prove 3 of these methods actually decrease the interaction. And we can use the experiment to prove 5 of these methods to decrease the interaction. Based on above analysis, we design a new loss function to directly penalize interactions in order to improve the adversarial transferability. Our method achieves the best performance in boosting the adversarial transferability. Thank you very much for your listening. I believe that the current Xci research is far away from science, and it requires us to go a long way to push current Xci studies towards science. But it's worth it. Thank you very much.